Hey, Harsh here. When you type something into ChatGPT or Claude and it answers, what is actually happening in there? Not the marketing version, but the real version, the matrices, the math, and the thing that GPU is doing literally billions of times a second. I want to be honest with you because most of the explanations I see about LLMs are quite unsatisfying. They either stay so high level that you learn almost nothing about it, or they drop you into the original paper with 8 heads of scale dot product attention and no map. We're going to do a thing that is a little bit in between. I'm going to go through every concept in order with some actual numbers so that we are able to understand this concept a little better. A large language model is a next token predictor. That's it. That's the whole machine. Everything we build today, tokens, embeddings, attention, the training, exists to make that one prediction better. A language model takes in some text and produces a probability distribution over what token comes next. That's the entire job. For example, I give it the capital of France is, and it doesn't know the answer in any human sense. It produces a list. Paris 91%, the 3%, located 2%, and so on across its entire vocabulary. Then it picks one, usually a likely one, and appends it to the input and runs the whole thing again to get the next token. Is Paris goes back in, and now it predicts a period or a new line. This is called autoregression. The model's output becomes the part of its next input. When ChatGPT writes you a 3 paragraph answer, it is not composing that answer as a whole. It is making this single next token guess over and over and over, hundreds and thousands of times, each one informed by everything generated so far. All of this impressive behavior, solving math, writing working code, holding a conversation, falls out of optimizing this one boring objective at a huge, massive scale. Nobody programmed grammar rules, nobody wrote a translation module. The model learned that being good at predicting the next token, and that requires internally modeling grammar, facts, and logics. There are generally 5 stages. First one is tokenization. Your text gets chopped into chunks called tokens, and each chunk becomes a number. Second is embedding. Each number becomes a vector, a long list of numbers that encodes meaning, and we stir in where the token sits in the sequence. Third is a transformer block. This is like the core of the LLM. Each block has 2 parts, an attention layer and a small neural network. And we stacked this block many times. It was 12 times in GPT-2, very, very old times, and 96 times in GPT-3. Fourth is un-embedding. We take the final vector and convert it back into a score for every token in vocabulary. Fifth is sampling. We turn those scores into probabilities and pick one. And this is the loop from the last slide. We feed the chosen token back to the start and do it all again. The model never sees the word strawberry. It never sees letters at all. Before any text touches the network, it gets shattered into tokens. A token is just a chunk of text, sometimes a whole word, sometimes a piece of one, sometimes just a space plus few characters. The model has a fixed vocabulary of these chunks. For GPT-2 and 3, that was 50,257 of them. Every token has an ID, an integer, and that's what flows in the network. How does it decide the chunks? An algorithm called byte-pair encoding. Start with the raw bytes. There are 256 possible byte values. So that's your base alphabet. Then look at your training text and find the most common adjacent pair of symbols and merge it into a single new token. Repeat this tens of thousands of times, and frequent patterns like the or ing or GPT own their own token. Rare stuff stays broken into pieces. It's quite elegant that the model spends its vocabulary budget where the language actually clusters it. Notice that ChatGPT spills into chat and GPT, and strawberry splits into straw and berry. And this is exactly why, for years, these models couldn't tell you how many R's are there in strawberry. They literally cannot see the individual characters inside a token. They see two opaque chunks. We will come back to that because it's the cleanest proof that tokenization is doing something deeply non human. For now, text in and integer IDs out. Okay, so we have these integer IDs, but an integer like 39,752 carries no meaning. The token 39,752 isn't bigger or more than the token 39,751. So the first thing the network does is convert each ID into a vector, a long list of numbers. In GPT-2, that list was 768 numbers long. In GPT-3, it is 12,288. This is just a lookup table. ID number 39,752 grabs row 39,752 of a giant matrix. This matrix has one row per vocabulary token. So 50,257 rows by 768 columns, that's already 39 million numbers. All of them learned during training. Now, why a vector? Because a vector has a direction, and direction is how the model stores meaning. Take the embedding for king, subtract the embedding for man, add the embedding for women, and you land almost exactly on queen. The model discovered this on its own, that there is a royalty direction and a gender direction in this space. And this placed words so that the geometry encodes these relationships. So when I say the model understands a word, what I concretely mean is that it has a point in its 768 dimensional space, positioned so that the meaning becomes distance and relationship becomes directions. Every token in your prompt is now a point in the space, but there's a problem, and it's a big one. So far, the word dog gets the same vector whether it's the first word or the last. The model has no idea about its order, so we need to fix that. The transformer, the engine that we are about to build, looks at all of these tokens at the same time in parallel. That parallelism is the whole reason these models are so fast and trainable at scale. But it comes at a cost. The raw mechanism has no concept of order. To it, dog bites man and man bites dog are the same bag of three vectors. That's obviously fatal for a language, so we fix it by literally adding positional information into each token's vector before it enters the stack. Each position, first, second, third, gets its own signature, and we add that signature into the embedding. Now, the vector for dog in position 1 is slightly different from a dog in position 5. The network can tell them apart. The original transformer used sine and cosine waves of different frequencies. Think of it like a clever binary clock made of smooth waves where each position gets a unique pattern. It's clever because the model can learn to compute relative distance from it. But most of the modern models use something called rotary positional embeddings. Instead of adding a pattern, it's a rotate search vector by an angle that grows with position. The further along the token, the more rotation. This turns out to handle long chunks much more gracefully, which is part of why context windows exploded from 2000 tokens to 100,000 tokens. Either way, the point is the same. We have stamped each vector with where it lives. Now, finally, we are going to learn about transformers. This is the heart of everything. And the beautiful thing is how simple the repeating unit is. One transformer block does exactly two operations. First, attention. This is where tokens are allowed to look at each other and pass information around it. The word it reaches back and pulls meaning from the animal earlier in the sentence. Tokens are talking. Second is a small neural network, a multi-layer perceptron, the MLP, applied to each token on its own. After a token has gathered context from its neighbor, this is where it sits and processes the information privately. It has no talking, just a lot of thinking. That's the entire block. Gather then think, attention then MLP. And then this is the key move. We start this identical block over and over and over, 12 times in GPT-2 and 96 times in GPT-3, and this number keeps on increasing. The output vectors of block 1 become the input vectors of block 2, and so on up the tower. But what does this stacking do? It is the depth of abstraction. In the earlier blocks, a tokens vector might just encode this is a noun, it's about an animal. By the middle, this is the subject of the sentence, and it's the thing that was tired. And near the top, genuinely abstract stuff, tone, intent, what's likely to come next. Each block refines the meaning a little more using context. Two operations repeated again and again, and that's a transformer. Now let's actually open up the first one, attention, because that's the idea that changed everything. Here's a sentence that everyone uses because it's a really good example. The animal didn't cross the street because it was too tired. When you read it, you instantly know that it means the animal, not the street. But how does the model know that? Attention. The idea is that each token gets to look around and decide which other tokens matter to it right now. And it does this, and they do it with three vectors that every token produces: query, key, and value. Think of it like a search. The query is the token that you're looking for. The token it basically broadcasts a query that I am a pronoun, I am looking for a noun to refer to. Every other token produces a key, a little advertisement for what it is. Animal has a key saying that I am a concrete noun, an entity. And when its query lines up well with animal's key, you get a high relevance score. And then there is value. The value is the actual information the token will hand over once it decides that animal is relevant. It pulls in a big chunk of animal's value sector and mixes it with its own representation. After this step, the vector for it literally contains a piece of animal baked into it. That's attention in, plain English. Every token asks a question, every token answers with an advertisement, and the information flows from the relevant tokens to the asking token. Now, how is this actually computed? Because it's just an elegant formula and you already know all the pieces. Don't let the formula scare you. You already understand every single symbol. Attention equals softmax of q times k transpose divided by root dk all times v. Let's walk from left to right. Q times k transpose. Q is the stack of all the query vectors. K is the stack of all the keys. Multiplying them is just taking the dot product of every query with every key. And remember from school, dot product is large when two vectors point the same way. So this step produces a grid of scores for each token, how relevant it is to every other token. That grid is the attention pattern. Divide by root dk. Dk is the dimension of the key vectors, 64 in the original transformer. But why divide? Because when you dot two 64 dimensional vectors, the result can get large, and large numbers fed into next step, softmax, cause it to saturate. It goes flat, the gradients vanish, and the model stops learning. Divide by root dk keeps the number in a healthy range. It's a small detail with a big training impact. Softmax. This takes each row of the raw score and squashes it into a clean weights between 0 and 1 that add up to 1. Now, each token has a proper distribution. I will put 70% of my attention on this token and 20% on that one. Finally, times V. We take those weights and compute a weighted average of all the value vectors. The tokens you attend to most contribute the most. The output is a new context enriched vector for every token. That's one formula, and that's what attention is generally. So, this one attention pass is good, but it forces every relationship to share one channel. Language has many kinds of relationship happening all at once. Whom refers to whom, which verb goes with which sentence, and what tense are we in. So we don't run attention once, we run it many times in parallel, and we call each parallel copy a head. Each head gets its own query key and value matrices, so each one learns to specialize. Researchers have actually poked inside training models and found heads that do remarkably interpretable things. One head reliably connects pronouns to their nouns, another tracks previous tokens, another links opening and closing brackets in code. Nobody told them to. They specialized because it helped in prediction. And the bookkeeping is very neat. In GPT-2, the embedding is 768 dimensions and there are 12 heads. So each head works in on a 64 dimensional slice. 12 heads each do their own attention on their slice. So you concentrate the results back into 768 dimensions and the final projection mixes them. GPT-3 cranks this to 96 heads. So picture it like reading a stack of colored highlighters. One highlighter marks pronoun references, one marks subject verb pairs, one marks the tense cues. Each head lays down its own highlighting, and when you overlay them, you get a genuinely rich, multi relational picture of the sentence. That's multi head intention, and that's one more rule we have to add, or the model can cheat. During training, we show the model entire sentences at once so it can learn efficiently in parallel, but the model's job is to predict next token. While predicting token 5, it's allowed to look at token 6, the actual answer. It learns nothing, it just copies the future. And that's cheating. And it would make the model that's perfect in training and useless in reality. To fix that, there is something called casual mask. In attention grid, before we apply softmax, we take every score where a token is looking at a future token and set it to negative infinity. After softmax, negative infinity becomes a weight of exactly zero. So every token can attend to itself and everything before it. But the future is invisible. Geometrically, you can keep the lower triangle of attention matrix and throw away the upper triangle. This single decision choice is what makes GPT a generator, and comparing it to a BERT, which is an encoder, BERT lets every token see every other token in both directions. That's fantastic for understanding a sentence that you already have, like for search or classification, but it can't write text left to right. GPT GPT's masking gives up the bidirectional view in exchange for ability to generate one token at a time, never seeing what it has written yet. That constraint baked into math is autoregression. Now let's leave attention and look at the other half of the block, the part that holds most of model's knowledge. People obsess over attention, and that's fair enough. It's a very beautiful and famous part. But attention is only about a third of model's parameters. The bigger chunk lives in the next piece, which is the feed forward network. And it does something completely different. After attention, every token has gathered context from its neighbors. Now, the feed forward layer takes each token one at a time with no further mixing and runs it through a tiny two layer neural network. And the pattern is take the 768 dimensional vector, blow it up four times its size, so 3072, apply a non-linearity, then squeeze it back down to 768, then expand and contract is where a huge amount of models actual computation happens. And what it computes, uh, interpretability researchers increasingly think of this layer as a kind of key value memory. a place where facts are stored and looked up. The expanded middle layer has thousands of neurons, and specific neurons fire for specific concepts. When the context says the Eiffel Tower is in, some neuron pattern here helps retrieve Paris. The knowledge the model has, capitals, dates, code syntax, who wrote what, is largely encoded in these weights of these feed forward layers distributed across the stack. So, attention is communication, the part where tokens talk and share, and the feed forward net is kind of the computation, the part where each token sits alone and processes what is heard and pulls on the stored knowledge. Now, let's talk about residual connections. Around every sublayer, every attention, every feed forward, we do something tiny. We take the input, let the sublayer compute its output, and then we add the input back to the output. That's it. But it matters a lot. And there are two reasons for it. One, it gives information a clean path. A token's core identity can flow all the way up to the stack without being mangled, while each layer adds refinements on top. Second point, it gives gradients a clean path backward during training. In a deep stack without residuals, gradients can shrink to zero as they travel back, and the early layers never learn. Residuals, which came from ResNet image models in 2015, create a gradient highway. They are a single reason we can stack 96 layers instead of 6. Picture one vector per token flowing straight up the entire model like a conveyor belt. Each attention and each feed forward block reads from that stream, computes something, and writes its contribution back by adding it on. The stream accumulates meaning as it rises. And second layer, normalization. Every time we do a computation, the numbers in these vectors can drift, get too big or get too small or lopsided. So layer norm recenters it, rescales them at each step so everything stays in a stable range. Without it, deep training is nightmare of exploding and vanishing values. Together, residuals and layer norm are the things that hold everything together. So we have our block, attention, feed forward, wrapped in residuals and layer norm. Now we just do the obvious thing. You have to repeat it. 12 times in small models, 96 in GPT, and more than 100 in today's frontier systems. Identical structure, different learned weights in each. As a vector climbs this tower, something remarkable happens to what they represent. Down at the bottom near the input, the model is working with surface level stuff. This is a noun or a verb, basic grammar, local patterns. As you move up through the middle layers, the representation captures relationships. This token is the subject. This one refers back to that earlier entity. This clause modifies the noun. And by the top layers, the vectors encode genuinely abstract prediction focused features. The tone of the passage, the intent, the what kind of word should possibly come next. This is kind of a refinement pipeline. Each layer takes the meaning so far and sharpens it using context over and over and over hundreds of times. Nobody designed those intermediate concepts. They emerged because to predict the next token, we look at the vector for the final token in the sequence as it comes out of the top stack. That one vector have absorbed the entire context through all those layers of attention and and the model is complete distilled summary of given everything so far. Here's my state of mind about what comes next. Now we just have to turn that vector back into words. So you got one vector at the top of the stack that summarizes everything. But it's still just a list of 768 numbers. What we want is which token comes next. So what we do? So we do the mirror image of the embedding step at the very smart. Remember the embedding matrix turned a token ID into a vector. Now the un-embedding matrix turns a vector back into scores over tokens. We multiply our final vectors by this matrix and out comes one number for every token in the vocabulary, 50,257 numbers. Each one is called a logit and it's a raw score. how strongly the model favors that token as the next one. The token Paris might get a logit of 14.2, London 6.1, and some random token a negative number. Many models tie these weights, meaning the un-embedding matrix is literally the transpose of the embedding matrix. The same learned table used both in directions. When they are separate, it's not cheap. In GPT-3, the un-embedding is another 617 million parameters all on its own. So now we have 50,257 raw scores, but scores aren't probabilities. They are not between zeros and ones. They don't sum up to anything in particular. So to make a decision, we need to turn these logits into a clean probability distribution. And that's one function you have already met today, used here for one more time. Last step of a single prediction, we have 50,257 logits, and Softmax turns them into probabilities. Every value between 0 and 1, the whole thing summing into 1. Now it's a proper distribution we can sample from. But how we sample is the real choice with real consequences, and it's controlled by a few knobs you've probably seen in API settings. First, temperature. Before Softmax, we divide the logits by temperature. Low temperature makes the distribution sharp and peaky. The top token dominates. Output is focused and repetitive and almost deterministic. High temperature flattens the distribution. Lower probability tokens get a real chance, and output gets more surprising and creative, and also more prone to going off rails. Temperature is your dial between boring and reliable and wild and inventive. Then the selection strategy. Greedy just takes the single most likely token every time, fine for factual tasks, but dull and prone to loops. Top K says only consider the top K most likely tokens and ignore the long trail, then sample. The top P, also called nuclear sampling, is smarter. It takes the smallest group of top tokens whose probabilities add up to, say, zero point 0.9 and samples from just those. That way, the candidate pool grows when the model is uncertain and shrinks when it is confident. The only reason ChatGPT gives you a different answer on a reroll is this sampling step right here. This is where the dice lives in. Then we take our chosen token and append it and go back on the top. Let's connect the architecture to what you actually feel when you use one of these modules. That is left to right, token by token streaming. Why does it generate that way, and how is it fast enough to be usable? The naive version is to produce token 101, you would run a forward pass over 1 through 101, recomputing almost everything you just did. For a long conversation, this is catastrophic. So, the trick is KV cache. Look back at the attention. Each token produces a key and a value, and crucially, a past token's key and value never change as you add new tokens. So, computing them once and storing them. When you generate a new token, you only compute that one token's query key and value, and you let its query attend against the entire cache of stored keys and values. You never recompute the past. This splits generation into two phases with very different personalities. Prefill, you process the whole prompt at once in parallel, filling the cache. This is compute heavy. It's why there is a delay before the first word appears. Then decode. You generate one token at a time instead of reading the whole cache. This is memory bandwidth heavy, and this is why text streams out at a steady pace. Two practical consequences that you should know about this is that one, this is exactly why output tokens cost 3 to 10 times more than your input tokens on every API. Input gets processed in one efficient parallel stream, and output is paid for one expensive sequential step at a time. Two, the cache grows with every token, and the attention cost scales with the square of the sequence length, which is why huge context windows are genuinely expensive to serve. The architecture and the pricing are the same story. We have been talking about weights, the embedding metrics, the attention matrices, the feed forward layers. hundreds of billions of numbers, but where do they come from? Nobody types them in. They are learned, and learning processes conceptually simple, just done at an insane scale. You start with all the weights set randomly. At this point, the model is pure noise. Feed text and it will predict garbage. Now you do the following over and over. Take a chunk of real text from the training data. At each position, have the model predict the next token. Compare its predicted probability distribution to the token that actually came next, and measure using a measure called cross entropy loss. Basically, how surprised was the model by the truth? High surprise, high loss. Then backpropagation, you compute for every single weight which direction to nudge it to make the correct token slightly more likely next time. Gradient descent takes that tiny step. One example barely moves anything, but when you do across trillions of tokens of text, and the weight slowly organizes themselves into a model of language. Grammar, facts, and reasoning patterns, all of it gets pressed into those matrices because all of it helps to reduce next token surprise. GPT-3 saw on the order of 300 billion tokens, and today's models are multiple trillions. Thousands of GPUs running from weeks to months, costing tens of millions of dollars. And there's a recipe for not wasting that money. The chinchilla scaling law showed that for a given compute budget, you roughly want 20 training tokens for every parameter. Get the balance wrong, and you have literally burned millions on untrained model. But notice what this gives you: a model that completes text, not an helpful assistant that takes one more stage. The thing that comes out of pre training is just the base model, and it is not ChatGPT. A base model is pure text completion engine. If you give how do I bake bread, it might continue more questions because on the internet, questions are often followed by more questions. It's not trying to help you, it's trying to predict possible. It will cheerfully continue into toxic or false content because that exists in the training data too. It has no values, no notion for being an assistant. Turning that into something useful is called post training, and it has two main moves. First, supervised fine tuning or SFT. You hand the model thousands of curated examples of the behavior you want, a question, then the ideal answer, and continue training on those. Now it learns the format being a helpful assistant. See a question, predict a direct answer. Second, and this is the famous one, RLHF, reinforcement learning from human feedback. You generate several responses to prompt, have humans rank which is the best, and train a separate reward model to imitate those human preferences. Then you optimize the LLM to produce responses the reward model scores highly. Over many rounds, the model gets nudged towards being more helpful, honest, and harmless, and towards refusing things it shouldn't do. And none of this changes the architecture. It's the exact same next token prediction engine we just built. Post training doesn't give it new abilities so much as to steer the abilities pre training already created. It is the same engine, just pointed in a more useful direction. Now that we have gone through the entire LLM, the strengths and the failures, and I hope it's now that you have seen the whole machine, the strength and the failures stop being so mysterious. They are both the direct consequences of one objective. Why is it so capable? Because predicting the next token across the entire internet is a very demanding task. To do it well, the model was forced to learn grammar, facts, arithmetic patterns, code structure, even rough reasoning, because all of those reproduce friction error. The capability is the side effect of being relentlessly optimized on one simple goal at an insane scale. But flip it around, and the failures are just as logical. Why does it hallucinate? State the false things with total confidence because it was trained to produce possible continuations and not the true ones. A fluent, confident, wrong sentence is often a perfectly low loss prediction. The truth was never directly in the objective, possibility was. Why can't it reliably count R's in strawberry? You already know it never sees letters. It just sees tokens, straw and berry. Asking it to count letters inside a token is like asking you to read a word painted on a card you're not allowed to look at. The newer reasoning models get it right, mostly by learning it to spell the word token by token first and then count. And why does it have no memory of a last conversation? Because each request is a single forward pass over whatever is in the context window. There is no persistent state between your calls. If it's not in your prompt or the system's context, it doesn't exist to the model. Once you see the mechanism, it's magic and the limits are the same thing viewed from two different sides. Hey, if this video helped you understand this topic, don't forget to like and subscribe. You can also drop your suggestions down in the comments about the improvements and the topics you would like me to cover next. Till then, thanks for watching, and I will see you in the next one. Peace.